Let's take a look at the code, starting with the overall organization of the solution. So we have the solution with 10 projects, the bindings. So the projects under the bindings folder are Maui libraries for WebRTC for the various native platforms, Android and iOS. And then we have RT Flow, which is the real-time multi-agent framework. These projects are for the real-time OpenAI API. And then here are some samples. So there's a minimal sample. And then the sample that we're discussing right now is RT.Assistant. Okay, now let's walk through how the Prolog engine is integrated into the application. So I'm going to open up RT.Assistant, go to Resources, Raw, and then www root. So this is the Prolog engine, Tau Prolog. It's a JavaScript file. So in Maui, there's a control called hybrid web view, and you can run local web content in the hybrid web view. So this JavaScript engine is loaded into the hybrid web view. Um, there are some other JavaScripts required. So the hybrid web view.js serves as a bridge between .NET and the hybrid web view JavaScript. So you can send messages back and forth using this. The bridge.js is basically the API into the JavaScript engine from .NET. So this is where you actually evaluate the Prolog query. And the hybrid web view itself is under views. So if I open the main page, which is called chat.fs, I will scroll down to where that is located. So the hybrid web view that I was talking about is in the UI. So basically, you have to load the browser into the UI, and then you can communicate with the JavaScript portion of the browser using the JavaScript files we have here. Okay, now let's take a look at the Prolog itself. We have been talking about Prolog facts or the Prolog plan database. What does that look like? So under RT.Assistant, under resources and raw, there's www root, and that's where all of the JavaScript is housed. But along with the JavaScript is the Prolog file for the plan clauses. So you can think of this as the plan database. Now each line here is the clause for a particular plan. There are about 15 plans, and if I fold the text here, you can see that each plan is fairly rich. So there's a lot of content associated with the plan, the prices, the features, the different attributes of the features, and so forth. Now, in addition to the plan database, there's another file, plan schema. So this is a file that just contains the plan structure. It's not an actual plan clause, but it's a kind of a template. So it sort of defines the overall structure, what are the features, what are the attributes of these features, and it defines all possible features that are available in a plan. And the idea here is that you use this file as part of the code gen process for to tell the LLM what the plan fact looks like. So based on this, the LLM will generate correct Prolog code to query the plan facts database. So earlier we looked at the implementation of the RT flow for this particular sample. There are four agents: app, codegen, query, and voice. They exchange messages with each other. The internal state of the agents and the flow is private. They can only communicate with each other via strongly typed messages. Okay, now let's take a look at how these strongly typed messages are defined. So there are two types here: the flow message, which has these union types: FL start, terminate, and usage. So these are messages that are sent to the flow. So you can start the flow, terminate it, and also you can send usage messages to accumulate the token usage for cost analysis and so forth. Now, this is the agent message. The agent message is broadcasted on the agent channel. There are all different types of these messages. Typically, you use discriminated union types in F-sharp pattern matching. So let me take a look at this message here, Prolog. So this is where Prolog code is generated and broadcasted on the bus. So if I say find usages, it'll give me, one of the usages. There's several there. So somebody sends the message, the other agents pick that message up. So in this case, we have the app agent picking up the Prolog code message to basically display the Prolog code in the UI. So this is the pattern matching syntax. You have match, message, and then you can have a pattern over over which you want to match. So here we are matching with just a strongly typed discriminated union, but you can have more complex pattern matching. And if you may be handling certain kinds of messages, but you may want to ignore other messages. So this kind of pattern just ignores the message and doesn't do anything. Like it just returns a void in this case. Okay, now let's take a quick look at the four agents that we have in the system. So they're under the agents folder. So there is the query agent, codegen agent, app agent, and the voice agent. Now, this is the flow implementation. So this is the asynchronous state machine for the flow. So you start in this start state, and if you receive the start message, then you start the agents. If I go here, essentially you're starting all of the agents so they can start listening to messages and doing their function. Okay, so this is the voice agent. Now, when the voice agent starts, it's actually listening for two types of messages. So one type is coming from the RT flow system. So the RT flow bus, which is over here, and this is the part where it's listening to flow messages. But then it also listens to messages that are coming from the OpenAI real-time API. So it's essentially here in this case, it's starting two asynchronous computations that are running in parallel. If we look at the voice part, so this again has that similar pattern. You basically have a channel available to you. So here's the channel that comes from the WebRTC connection. And again, there's an asynchronous computation here to essentially read messages that are coming over that channel. and convert them into strongly typed wrappers, and then use this scan async with this update function to handle these messages. And if we look at the update function, you can see that it's handling explicitly handling these types of messages. You don't have to handle a lot, but for others, like for others, it's just logging them and not really doing anything with them. But if there's an error sent back by the API, it's crucial to sort of know about errors, because if the API sends an error, then the API is in a state that it may not work as expected. The other messages that you have to really handle are session messages, session was created or updated, and then any tool calls. So these are messages for tool calls. This is a message. When this message arrives, this function will determine whether it's a tool call to basically run the natural language query, or it's a tool call to get plan details, and then in this particular case, it's just broadcasting that appropriate another message on the bus for another agent to pick up and handle those messages. Okay, now let's turn our attention to how we build UIs in F Sharp. Before looking at the application code, let's just understand how UIs are built in F Sharp in general. So F Sharp uses a system called Elmish, which is an implementation of functional reactive programming. And in fact, the famous library from Meta, React, is also a functional reactive programming library. In functional reactive programming, you have your UI components are functions, and these functions are triggered whenever application state changes, and essentially the UI is updated whenever these functions run. Now I'm going to walk you through the simple Elmish system. So typically in Elmish you have a model which holds the application state. So here we have just a count as the application state. Also in Elmish you have messages, so which is typically an F-sharp discriminated union type. We have two unions here, the increment and decrement, and this is the UI control as a function. So this is the name of the function. It accepts a parameter called model, and here's the interesting part. This is a V-stack control, a vertical stack control, which is stacking an image, a label which is whose value comes from the model count, and then the two buttons, increment and decrement. So when this, let's say this increment button is clicked, it'll generate a message. It'll send this message into the Elmish system. So the Elmish system essentially collects these messages, serializes them, and then calls the update function. In the update function, you basically do a pattern match, and depending on what the message is, you update the application state accordingly. So in the increment case, we are incrementing the count, which will change the application state, and then it'll re-render the UI. Now there's more sophistication here. There's double buffering or to make sure that the UI changes are smooth. But essentially, conceptually, this is how you build UIs in F Sharp. Here is the actual UI code, starting with the model. So you have the model type. It has several fields. One is this log. So anything you see in the log is part of this list. The session state determines the color of the on-off button, and then you have the message type here. The update function This is the update function, so it's doing pattern matching over the messages and taking appropriate action. Sometimes the model is updated, sometimes other things happen, that are primarily in the background. But for Elmish applications, one good place to understand what the application is doing is to look at the update function, because that's the sort of the central control of how everything is being managed. I'm going to walk you through how the main page of the application is constructed. So on the right, we have the actual main page in the running application. It's in the chat.fs file. So let's take a look at what's happening. So there's several subviews. So this is the main view here. In the main view, we have a grid that basically renders three subcomponents. So these are the three subcomponents. So there's the controls view, the log view, and the header view. So the controls view is this view on the left, where you see these edit boxes with Prolog in them. And then the log view is this view on the right. This is where the log messages show up. And then we have the header view, which is the top bar that you see over here. So if I click on the header view and expand that, it's also another grid with buttons. So there's this button here, which is the show the settings. If I click this, this button will send the show settings message, which will then pop this settings window, which is another control. And here you can enter your secrets, like the OpenAI key and the Anthropic key. And there's also a checkbox. If you want to use Sonnet for code generation, you can check this one.